My name is Shaleen, and today I will talk about some of my recent work on compressed representations of conjunctive query results, and this is joint work with Paris at UW-Madison. So many data processing pipelines, they contain query workloads where the queries are instantiations of a specific access pattern or template. So this could be a fixed join query where the actual constants in the predicate are changing in the entire workload. So for example, a data analyst may be interested in finding the mutual friends of two different users, P and Q, and the entire workload consists of queries where the actual values of P and Q are changing. So this could be views that are repeatedly accessed by multiple queries in the context of multi-query optimization. And of more recent interest is the application of finding graphical insights over relational data. An example of this is, suppose that you have a DBLB relation, you want to find all the co-authors for a given author A, and your workload is all the queries where the value of A is changing. So in all of these cases, if you want to answer these queries fast, you can materialize the answer to these queries ahead of time. But materializing and storing the answers can be very expensive to store and compute directly. So for example, if we have our mutual friend query, which is essentially a triangle query, if you store the answer for all possible input PQ pairs, you will require D to the 3/2 space in the worst case. So the question we ask is it possible to make use of this workload information to create some data structure so we can answer query results efficiently? So let's look at a more detailed motivating example. So suppose we have our binary relation where every tuple AB means that user A is a friend of user B. And the data analyst wants to access this relation via the mutual friend query. So the data analyst will actually give you the values of X and Z, and we have to return the answer, which means we are enumerating all the mutual friends Y. So this can be expressed by the following query, and as I mentioned, so for any given instantiation of this access pattern, the values of X and Z are fixed by the user. And here Y is the free variable over which we are enumerating the output. So in other words, X and Z here are the bound variables, and Y here is the free variable. So given this mutual friend query, our goal is to answer any instantiation of this query as fast as possible. So what can we do here? So here are two possible extremal approaches. So first is we do nothing. So we run every query from scratch. So the good thing about this approach is we require no extra space. But the bad thing is that you may require linear time to even find out whether the output is empty or not. And in the second case, you could materialize the output for all possible input XUV pairs and then index them. So the good thing here is that we get constant delay enumeration because everything is essentially materialized. But the bad thing is that you require D to the 3/2 space in the worst case. So the main question we ask is it possible to characterize the space-time trade-off between these two extremes? So let's look at a very interesting data point in this entire trade-off, which is given by factorized databases. So suppose that we have the following query. So here all of the variables are free. So this is just the normal triangle join. So factorized databases tell us that in time D to the fractional hypertree width, we can create a compressed representation that takes the same space and do the enumeration with constant delay. But suppose that D to the fractional hypertree width is too much space. We do not have this much space available. So the question is it possible to trade off the constant delay requirement for a lower space requirement? And the second question is, can we say something interesting when we know about the access pattern? So the factorized databases result is applicable to all conjunctive queries. It does not care about what the access pattern is. But in our case, if we have some extra information that some of these variables will be bound, can we make use of this information and say something interesting? So to give you a brief glimpse of what our results looks like, so here we have our mutual friend query. So we've already seen that if we evaluate all of the queries from scratch, we require linear space, which is the space required to store the input. But in the worst case, you require linear delay to answer any possible instantiation of this query. If you materialize and index the answers ahead of time, you require D to the 3/2 space in the worst case, but now you get constant delay. And as a result of constant delay, the answering time for any particular instantiation is just the time required to enumerate the output. And our results are of the following form. So the user can pick any particular value of tau, which will give you the delay guarantee, and the space requirement and delay are now a uniform trade-off based on whatever value of tau is chosen. So over here, out is the output of the specific instantiation of the query, and the tilde notation is hiding some polylog factors. So here is the outline for the rest of the talk. So I will precisely define what our problem setting is. Then I will describe our main result and how we construct the data structure. Then I will discuss some limitations of applying our data structure directly and how we can remedy them using query decompositions. And finally, I will end with the future work and the conclusion. So let's look at the problem setting. So suppose I have a static database D, and I have been given my access pattern Q as the input, and I have compression time Tc. So in this compression time Tc, my goal is to create a compressed representation that takes space at most S. All of this is happening in the pre-processing phase. And once I am done with creating this compressed representation in Tc time, then the online phase will happen where the user can come in and can ask any particular instantiation of the query. So the user will plug in the values of the bound variables, and we have to enumerate the output. So the goal here is to construct a space-efficient representation that can help us answer these access requests. And we will study the trade-offs in terms of the following parameters. So we will look at the trade-off between the compression time, the space requirement of a data structure, and the query answering time. So here we will consider two different notions of query answering time. First is the delay requirement that we want for any particular instantiation of the query. And by delta delay, I mean the maximum time difference between any two consecutive output tuples should be bounded by delta, as well as from the beginning of the procedure to the first tuple and the last tuple to the end of the procedure. And the second notion is that of the total answering time for a specific instantiation of the query. So note that if I have the delta delay requirement, then the total answering time is trivially bounded by delta times out. But we will look at cases when we can say something better. So we want to say something better than just the trivial delta times out guarantee. So let me formally define what the access patterns and add-on views are. So in this work, we consider the class of conjunctive queries. So here is an example of the triangle query. So an add-on view is basically is a mapping of the variables in the head of the query to either bound or free. So they're mapped to either B or F. So as an example, for this particular triangle conjunctive query, this is one possible add-on view where X and Z are the bound variables and Y is the free variable. So this is the mutual friend query that we saw. This is the second possible add-on view where all of the variables are free. So this is just the normal join enumeration. So a special case of add-on view is when the add-on view is full. So a full add-on view is when all of the variables that are present in the body of the query are also present in the head. So that means there are no projections. So for the rest of the talk, I will focus on fully add-on views, and I will briefly return to this question on what happens when the view is non-full. So let's set up some technical machinery that we will require. So it will be convenient if we view our add-on view as a hypergraph. So let's look at an even more simpler example. So here I have my two-path query where X and Y are the bound variables and Z is the free variable. So this is what the hypergraph would look like. So X and Y are my bound variables, Z is my free variable. So the first notion that we require is that of the fractional edge cover. So a fractional edge cover is a weight assignment to all of the hyperedges such that for every variable, the sum of the weights of the hyperedges that include it is at least 1. So as an example, for this particular two-path query, we can assign a weight of 1 and 1 to both of the hyperedges, and it covers all of the variables. The second notion that we will require is that of a slack. So a slack is defined with respect to a set of variables. So the slack alpha S here is the largest positive quantity such that if I scale my fractional edge cover by this particular value, it is still a valid fractional edge cover for the variables in S. So let's look at an example. So suppose here I want to compute the slack for my free variable. So the slack for my free variable here will be 2. Why? Because if I scale down the fractional edge cover of 1 and 1 by a factor of 2, so it becomes half and half, but it is still covering the free variable. So half and half will still sum to 1. It is covering Z, even though it is not covering X and Y. So note that by definition here, the slack is a positive quantity, and it is at least 1. So it will be a quantity which is greater than or equal to 1. And the last building block that we will require is that of the AGM bound. So given the fractional edge cover, we can upper bound the output size of the query using the AGM bound. So in this example, when we have 1 and 1, the AGM bound will tell us that the worst case output size is t squared. So let's look at our main result. So here is our main result. So given a fully adorned view Q and a fractional edge cover U, the user can pick any value of tau, and then we get the following trade-offs. So the compression time is the AGM bound. The space requirement of a data structure is AGM bound divided by tau to the alpha. And then using this much space, for any particular instantiation of the adorned view, I get tau enumeration guarantee. And the answering time is the time required to enumerate the output plus this overhead of tau times out to the 1 over alpha. So alpha of VF is the slack with respect to the free variables. So there are 2 points to note here. First, the enumeration will be in lexicographic order, and the user can actually choose the ordering of these variables. So the user can actually tell what will be the output tuple format, and then we will enumerate in lexicographic order. And the second point to note is the space requirement during the pre-processing phase is also bounded by S. So it is not the case that we are materializing the entire worst case AGM bound output and then trying to do some compression. This is true compression in the sense that the pre-processing phase will also require at most spaces. So let's look at an application of the main result. So consider the star join query as shown here. So all of my red variables are the bound variables. Z is my free variable. And I will use the fractional edge cover as an assignment of 1 to all of the hyperedges. And note that here the slack for the free variable is n, because if I scale down my fractional edge cover by this particular value, it becomes 1 over n, but it is still covering the free variable because it still sums to 1. So applying the main result that I showed on the previous slide, these are the trade-offs that we will get. So in compression time d to the n, the space requirement of my data structure will be d to the n divided by tau to the n, and then I will get a delay guarantee of tau, and my answering time is the time required to enumerate the output plus the overhead of tau times out to the 1 over n. So let's look at how we construct our data structure. So the key observation is that worst case optimal joins, they already provide us an implicit delay guarantee. So what do I mean by that? So let's look at our 2-path example. So x and y here are the bound variables. So suppose that the user has fixed the value of x as a, fixed the value of y as b, and suppose my relation looks something like this. So in my relation, the degree of a is dA, so I have dA tuples. The degree of b is dB, so I have dB tuples there. And essentially what I want to do here is take these dA dB tuples and intersect them over the free variable z. So how much time do I require to do that? So the observation is that you require mean of dA dB time, because you can iterate over the smaller list and do hash lookups over the larger list. So if mean of dA dB, which is smaller than square root of dA dB, and if this quantity is smaller than tau, then we will get our tau delay guarantee. Because in worst case time tau, I will find out the output, or I can declare that there is no valid output. However, if for any AB the square root of dA dB is greater than tau, then I will have to store some extra information. So what I will do is the following. So we will decompose the join for all input AB where square root dA dB is greater than tau. We will decompose the join into multiple join subinstances. Each subinstance will achieve a delay guarantee of tau, and then we will build a binary tree that will help guide the execution of the query. So it will help us find the right instances where we need to evaluate the join. So let's see how we can construct that. So again, I have my 2-path query here. So suppose A is the domain of the free variable. So what I will do is create my binary tree in this particular fashion. So the root node contains the domain of the free variable. So in this example, I'll take the example as A to M, and then in this particular root node, I will pick a split point beta. So here, let's suppose the split point is beta. So I will partition this domain into 2 different halves. So the left node is A1, A to E, right node has the domain G to M, and then I will recursively keep doing this partitioning until I have O of log D levels. And I will come back in a minute to say how we do this partitioning. So once I have my binary tree, I will store the following information. So for any input AB, where square root of DADB was greater than tau, I will mirror the structure of this entire tree, and then for each node, I will store two pieces of information. First, I will store a bit of 1 for the given input AB if there exists at least one valid valuation in this domain such that this join condition will be satisfied. And the second piece of information that I will store is whether the cost of evaluating the join using the domain at that particular node is greater than tau or not. And then I will mirror this structure of the tree and then keep on storing this information at each of the nodes. So suppose at the second level, for this particular A1, I am storing a bit of 0 because there is no valid valuation for Z that satisfies this join condition. And once I know this, I don't need to store anything below this particular tree, below this particular node. And on the right hand side, I will again store this information. So I know that there is some valid valuation for Z in A2, and the join cost is greater than tau, so I'm storing these pieces of information. And I will keep on doing this. So at some point, I will reach a node, in this example, this is A4, where the join cost becomes smaller than tau. At this particular point, I can simply take the domain for Z and take the semi-join with respect to my DADB tuples. So I had my DADB tuples, I can take the semi-join with respect to this domain and then just evaluate the join. And by construction, I know that the join cost is smaller than tau, so this will give me my delay guarantee. But since I have log D levels, I have a logarithmic overhead, so this is where we get the logarithmic overheads from. So the split points in this particular structure are created in the following way. So this particular tree I have shown you here is for a specific AB. So there will be multiple such ABs, and the split points are chosen such that the number of bits I am storing in these two different nodes are balanced. So I make sure that this tree is balanced. So once I have done that, the final algorithm is given this AB. I will traverse this tree in pre-order fashion. And note that my domain here is sorted lexicographically. So I will traverse this tree in pre-order fashion and then keep on executing the join. And if I have some A prime B prime where the join cost at the root node itself is smaller than tau, then I don't need to store anything else. I can simply evaluate my join. So the final space requirement for the data structure is the number of bits I will store for all the AB where square root of DADB is greater than tau. And for a running example of 2-path, this is the trade-off that we get. So we get a delay requirement of tau, the space requirement is n squared over tau squared, and the answering time is out plus tau times square root of out. And more generally, this is what the trade-off would look like. So we can always get a linear trade-off between the space required by a data structure and the worst case delay guarantee for any possible instantiation of the query. But if the slack is greater than 1, then we get a trade-off which is better than this linear trade-off. So let's look at the limitations of this data structure. So consider this 2-path query where all of the variables are now free. So if I apply my data structure here blindly, it will tell me that I required n squared space for constant delay enumeration. But we know that this is suboptimal. This is suboptimal because this is an acyclic query, and we know that in linear time preprocessing, we can construct a representation where you can do constant delay enumeration. So what have we done wrong? So the key observation is we also have to use the query decomposition in conjunction with our data structure. So let's look at what these query decompositions are. So here is an example of a 6-path query. So this is a query with path length 6. So the query decomposition is a tree which satisfies these 3 conditions. So for this particular 6-path query, this is what the decomposition would look like. So each particular bag in the node is a subset of variables. Each hyperedge belongs to some bag, and all of the variables in this tree are connected. But for our purpose, we will require the notion of a C-connex decomposition. So a C-connex decomposition is characterized by this tuple t comma a, where t is the tree decomposition, and a is a connected subset of bags in this tree decomposition, such that if I union the variables in these bags, they union to exactly C. So as an example, for this particular 6-path query where my bound variables are x1, x5, x6. So I will fix my C to be the bound variables, and the root of this bag contains these bound variables. So this is my A in this particular example, and the rest of the tree is just the query decomposition. It respects all of these three conditions. So given this C-connex decomposition, what do I do now? So all we have to do is now apply a data structure to each of the bags that are present here. So what we will do is the following. For each bag in the C-connex decomposition, we will assign it a number delta I. And intuitively, this delta I corresponds to a delay guarantee of d to the delta I in this particular bag. So as an example, here I am assigning these delta I numbers to be half, half, half for all of the bags. So in each of the bags, I will apply my data structure, and for that data structure, the delay guarantee is d to the half. So intuitively, this is what is going to happen. I will start my enumeration from, I will enumerate this particular C-connex decomposition in pre-order fashion. I will reach this particular B1 bag. So for a given instantiation, for a given x1, x5, I will find a valid valuation for x4, x2, and this x4, x2 now acts as the bound variables for the next bag. So as I'm going down the tree, I'm discovering valuations for these free variables, which will subsequently act as bound variables for the bags which are below. So what is the overall delay guarantee here? So the overall delay guarantee for the query is largest root to leaf delay product, because the enumeration in each of the branches is independent. So I get d to the half delay in my bag B1, I get d to the half delay in my bag B2. So the overall guarantee will be the largest root to leaf delay product. There is a small issue here where I need to fix the data structures because I'm constructing these myopically. There may be a case where I generate an x4, x2, but this x4, x2 does not find a valid x3. But it turns out that we just have to do a bottom-up semi-join style algorithm where we can flip the bits so we don't make these kind of mistakes when we are doing the enumeration. So the question then becomes is how do I how do I assign these delta I numbers to each of the bags? So these are some complexity results. So given the adorned view Q and the C-connex decomposition, and suppose that if we have a space constraint, then in polynomial time we can find these delta I assignments such that the overall delay is minimized, and vice versa. If I have a delay constraint, then I can find these numbers delta I such that my overall delay guarantee is what the delay constraint specifies, and my space is minimized for this particular data structure. So future work and conclusion. So the first possible extension that we have to work on is what do we do when we have non-full adorned views. So non-full adorned views have a problem that we have to deal with deduplication, and we have already seen an example of this. So we have a DBLP query where we plug in the value of x and we want to find the co-authors. So now the problem here is for a given author, there are multiple ways to reach the same co-author. So we want to build a data structure where we can also handle this deduplication when we are doing the enumeration. The second possible extension is how do we handle more expressive patterns. So factorized databases are awesome because they can handle aggregations, they can handle ordering, they can handle regression-based tasks. So it will be a nice extension if we can also incorporate all of these tasks in our framework. And we have some preliminary results and ideas on how we can incorporate these things. And the third possible extension is to go away from these worst case bounds. So can we say something in expectation, or if we know what the query workload looks like, or if we know something about the data distribution, if it is Zipfian or if it is exponentially distributed, can we get some better guarantees if we know the distribution? And the final thing is obviously to build it, to see how these ideas work in practice. So that is all I had, and this is the teaser slide from this morning, which I will leave as the summary. Thank you. Yep.
So the constant delays seem to be the local fetish right now, but I think in practice what people would care about is the output time between them and the side of the output.
Right.
Does this give you more compression? In fact, if you don't care about constant delay, you just care about total output time. Does it enable you to get more compression?
If you can do that in the sense that if you have some idea about, if you can do some sampling to figure out what your output size would look like. So I haven't talked about how do you actually find these fractional edge covers, right? So it is possible to find a fractional edge cover that that minimizes the answering time by trying to maximize the slack, but that may blow up the delay. So it is possible to do a trade-off. So one result that we didn't include in the paper, we also didn't include in the full version, is if we have two different data structures with two different fractional edge covers, it is possible to get the best of both worlds. So for free, if you can optimize your fractional edge cover to find the minimum delay, but the answering time may be bad. You can find a different fractional edge cover which gets you a better answering time, but you can combine these two. So I think so. It's possible to do that for some interesting queries. So we considered this notion, yes. So it will help. So one thing that I didn't mention in my talk was something about the lower bounds. So there are some existing conjectures which tell us about the space delay trade-offs and what you can do here, which have, so you can show that the star join example that I showed you, it can be translated exactly to the set disjointness problem. So, and this is an example where you can use the notion of acyclic sequence, where you have just a two-path example. So, so our data structure can actually match these lower bounds. So in some sense, we are trying to do the best we can, assuming this conjecture is true. But the notion of slack does help for if you have those kind of notions where you want to project out some variables. The slack does help. Yep. So we haven't considered that at the moment, but that is again one possible extension. So related to that is also how do you actually build these data structures, right? So if it is nice if we can have the pre-processing time and then construct this data structure, but it may also be possible to build this data structure on the fly, where you can get some amortized bounds to show that you don't require AGM time in the actual world, but you can do something where you don't need to do extreme amount of processing that happens only for very few of the input values. But that is also an interesting thing to consider on what can we say about the lower bounds for this problem, which are open.